Working.
Sweet.
Yay.
Great. So thank you very much. It's a great honor to be here, Mars. Thank you for having me. Cody, I guess good luck. You are filling in big shoes now. So it's really, really nice to see that your community is growing and more people are joining it. And we're honored to be able to help the community and sponsor it. And because we ourselves are also community leaders. So we thought, how can we do a win-win situation for the communities? On the one hand, spread the word of what we're doing, and on the other hand, really give back to the community. And we hope that this will help you. So what I would like to do is really briefly, 5 minutes of your time to, it's going to involve some CLI and terminals and show you some cool stuff that they were doing. So it's definitely going to be very, very techy. So as I said, my name is Shimon Toltz, and I'm going to share my screen now. I'm one of the co-founders and the CEO of Datree. You're able to see my screen, right?
Yes.
Great. So a little bit about myself. So I myself am a CNCF organizer in Tel Aviv, Israel. Together with Itai Sakuri and other great members, we have the CNCF organization in Israel. Together with that, I'm very active within the cloud community, and I'm an AWS community hero. I run one of the largest communities in the world. It has 9,000 members of AWS. And in my previous roles, like my very last role was an engineering manager for an infrastructure division, and we had 400 engineers in the company. And this is where we felt a lot of the challenges that we're dealing with today. So what actually we do in Datree is we help prevent misconfigurations from reaching your production, from reaching Kubernetes. And we play along together with all of the tooling that you have today. So if you're using Helm, or if you're using different CI/CD solutions like Circle CI, GitLab, and so on, we integrate with everything. And it's an open source project that you can check out, the Trio/Datree. And the way it works is that you run the CLI utility against your configuration, and we tell you if you have misconfigurations. So it's very easy. I'll show you in a minute. And we're a Y Combinator company, YC, well-funded, over $10 million. And we have dozens of customers using our product. And I want to tell you my personal story of, how we got to this. Why did we even, go this road and open this company? So it all started when I was the engineering manager at my company, and a developer made a mistake. We all make mistakes. I also make mistakes, and our production went down. Okay, it happens. And then we made a post-mortem and we checked what happened and how did it happen. And we found the root cause. That's great. And then we said, okay, let's make sure this does not happen again. And then we asked ourselves, but how can we make sure this will not happen again? So we sent an email. We did like a small meetup in the company to tell people more about the problem that happened. But we already had, hundreds of engineers. Even if you have tens of engineers, it's not so easy. And we felt that this is not the way to do it. It has to be automated in the flow of the developers. And we really believe in a shift left approach. So let me show you how it looks like. So if you go to our website, it's very easy, datree.io. We really believe in, no marketing bullshit. It's just, directly the curl in order to install it. And when you click on Quick Start, you can see the docs. And the great value that you can get is, number one, we come with predefined policies. So once you install the solution, which is very easy, I'm just curling and installing the tree. It is now installed in my path. And now it becomes pre-configured with different rules that will run automatically when I execute my binary against the Kubernetes manifest. Now, of course, if I'm using Helm charts, I can use our Helm plugin. But just to show you, I'm running the tree test on a Kubernetes demo YAML file. And what you see now is that we're validating the YAML.
Shimon, sorry to interrupt.
I'm not presenting. Yes. You're right.
Yes,
You're right. I'm sorry. That's my bad. Thank you for telling me, Mars. So here, going back, so this is the website. And if we go, and you can just scroll the command, if we go to quick start, you get to our docs and you can see everything. So all we have to do is scroll the installation, and it's a one-liner and then it gets installed. And now let me execute a test against my Kubernetes manifest. And you will see that first thing is we validate that the YAML is actually correct. Secondly, we validate that the Kubernetes schema, and you can configure the version of the Kubernetes that you're using, and then the tree will check that the schema is compliant with the version of the Kubernetes cluster that you're running. And then we have different rules, like make sure that you have a memory limit, that you have a liveness probe, that you're using a pinned down version, and that it is not a, you're not using a Docker latest container. And of course, you can run this in your terminal, and you can also sign into our platform, and you can install it in your CI/CD. The way you do it is you just put it in your CI/CD, and then it will run there. And you will be able to use our dashboard in order to see the history of invocations. And the main benefit of it is that you get a centralized policy management. So you can go into the settings and enable and disable any policy you would like. You can change the description of every policy and change the communication with the developers of your company. So if a developer, if she makes a commit and runs the test, you can actually communicate and say, hey, read this internal wiki, or write your own message in order to communicate with the developers in your company through the terminal. So I hope this helps a little bit understand what we're doing. Obviously, you can check us out at datree.io, and I really encourage you to go and give us feedback and just try it out. Of course, there is a free tier, and unless you're a big company, it's not going to cost you much at all or anything. There's a very big free tier. So we really look forward to feedback, and go check it out. We have more than 30 policies, and I'd love to hear your feedback about the policies that we have. So thank you very much for listening and for having me here, and I'll hand it over back to Mars. Thank you.
Thank you.
Thank you.
It's great, Shimon. It's great. I can't wait to try it and to learn more. Thank you very much for presenting, and thanks a lot again. Our next presenter for today is Joe Stringer from. He will talk about from Observability. He will talk about eBPF and all the exciting and cool stuff happening there. So, Joe, thank you very much for coming here today. Yay!
All right, thanks, Mars. I'll share my screen. Hopefully, you'll see it up on the stream there. All right. It's off. Yeah. Up here. There we go. All right. Cool. So thanks everyone for joining and for giving this opportunity to speak to you today. So what I want to do with this talk is give you a bit of a glimpse into the power of eBPF, and dive a little bit deep into what Cilium is and how we're building on that power that eBPF provides to be able to establish like networking in your cluster, security in your cluster, and then the observability to be able to continue to run services in your cluster with confidence. Before I kick this off, like a little bit briefly about me. So I've worked in open source networking projects for coming up on about 10 years now. And about half of that, I've been looking at eBPF and what's going on here in this space. And over that time, I've seen it kind of go from this kind of curious kernel technology that a couple of, a random startup was kind of pushing into Linux. And it's just grown and grown and grown, and the power of what it can do and the size of the community that's really gathering around it, it's exploded. So what is eBPF? So you've probably heard that BPF is like a set of superpowers for your systems, for your clusters. But what is it? So simply, it's a tooling to attach business logic to pretty much anything that's running in your kernel. And so what this opens up is like a whole bunch of areas like security, tracing, profiling, networking, observability, all in a way that's safe and efficient, running inside your kernel, because the kernel sees everything, right? So there's a lot that you can do with BPF. I'm going to try and touch on a little bit and describe how it works, and then we'll get into some of the use cases later on. So how does eBPF work? So the OS kernel is typically event-driven. So what you have is you have events coming in from different like physical devices, virtual interfaces, network cards, storage devices, all these sorts of things. And then you also have like processes typically running in a user space, and they'll run on demand. Maybe they'll make some syscalls into the kernel. And the kernel is responsible for handling all of these events and managing the interactions with the system. So what eBPF does is it allows you to attach bits of business logic to these different events that are happening, regardless of where they're happening in that system. So, for instance, if your process wants to read a file out of the file system, then it'll issue that read syscall into the kernel, and then we can attach BPF programs there, right? Or later on, once we actually read that data back out of the I/O device, we can attach BPF programs there. Maybe your process is, making calls across the network and wants to connect to some destination. We can see that syscall going on. Or, at the packet level, we can see when the system sends an individual packet, we can attach BPF program there and maybe control the way that those packets are being forwarded. And not only that, when different events happen in the system that you might not expect, like, for instance, if packets are dropped in the network and you get a TCP retransmission, we can attach eBPF programs to those events in the system as well, and really get that deep context of like what happened in the kernel, like where did it happen, and then bubble that context up so you can, you have the context to be able to both control and observe and debug really what's going on in your system. So how do we get that context into eBPF? So eBPF is like a custom program that you're attaching to some event in the system. But the eBPF program has access to the stable kernel API, which we call like a set of helpers, which are basically like function calls to access different data or manipulate data elsewhere in the kernel. So for instance, it could be stuff like you can access packet content if you're running on at the network level, or you can figure out what is the current process and thread IDs for the program that's running at this event. You can generate random numbers if that's something that's useful for your use case. So there's like a whole bunch of different access pieces of the kernel that you can access and then do something with that context. And so you're running these programs, you're now getting a bunch of information from the kernel. And then we can also store that information into what we call eBPF maps. So eBPF maps are really just a data structure. And there's a variety of different data structures that are exposed to eBPF programs. So let's say, like, for instance, the file system example we had before, right? If you have two eBPF programs running at the start of a read request and then at the end of a read request, you can imagine actually recording the start time and the end time and calculating the diff and figuring out the latency of disk writes. And then you could aggregate that information and store them into a map, which is then able to be exported into user space, maybe into your metrics dashboards and so on. So that's just like a simple example, but I like it because it really shows the kind of power of this abstraction. So there's a bunch of different map types that are available to BPF programs. So this can be stuff like hash tables, least recently used lists, ring buffers to try and send traffic into or information into the user space processes. But yeah, it's really like, how do you efficiently store that state in whatever way that makes sense to your application, and then like share that wherever you need it, whether it's other BPF programs that are attached to other events in the system or to the user space applications. So let's make this maybe a little bit more concrete. So what you'll see on your screen right now is an example, like a minimal example BPF program. And we're building on the events, the helpers, and the maps here. And I'll explain how. So you can see that on the first line, we've got like syscall, ret, execve. And so this signature is actually saying we're going to attach this BPF program to the execve syscall, which is executed anytime that a binary is run on the file system. And this is actually being executed on the return of that syscall back up to your user space application. A few lines down, we've got a BPF get current com. And so that's actually grabbing the name of that process. Now that we've executed that, we're starting to execute that program. Like, what is the actual binary name on the file system of that process? And then we're doing like a perf submit. So this is a little bit unintuitive, but what it's actually doing is it's taking that name and it's sending that along with some other information up to a user space process, which can then basically read off this ring buffer and see a series of events that say, this program foo ran, and then this other program bar ran. And so if you have a user space application attached to the other side of this BPF program, you could actually just see all of the programs that are running your system live as they happen. So this is kind of one like minimal example, but I still haven't kind of put together quite how that arrives into the kernel. Like this is just code at this point, right? So in this case, it's a C example. You could use something like Rust instead. But basically, we compile that that program into a binary on the file system, targeting the BPF instruction set. And then once we've compiled that program, we can load it into the kernel using the BPF syscall. So what the kernel does when it receives that program into the kernel is it first runs this verifier step. So what it's trying to check is like, is this program safe to run inside the kernel? If it's going to try and do null pointer to reference, or jump outside of the bounds of a structure and access random memory, or if it looks like it's going to run forever, then we're going to reject that from the kernel. But if the kernel is able to assess that this program is safe to run, then we proceed to the next step. And what we can do is actually JIT that program to the native instruction set of your actual machines. So why do we want to do this? This actually allows us to get native execution performance without having to understand or write like native code. And furthermore, since we've gone through this verifier step before we actually attach that program to that event in the kernel, it's actually safer than other approaches like kernel modules that you might otherwise use to try to solve this problem. A range of different supported architectures, you can see them there. So I guess, yeah, who's behind this? So Isovalent, along with Facebook and a few others, maintain the core of eBPF inside the Linux kernel. But that's just a few people out of over 450 individual contributors, and that's just in the Linux kernel eBPF tree today. And if you join us on ebpf.io/Slack, you'll actually see that there's thousands more people really interested in what's going on with eBPF, and sharing ideas and building new cool stuff using this technology. And so this is pretty powerful, but like, what kind of things can you do with BPF, or what kind of problems are people solving? So one quote I'll bring up, Nikita Shurkov from the Facebook traffic team said that every packet towards facebook.com has been processed by BPF-enabled applications since May 2017. So it's been over 4 years of like Facebook running this stuff in production. And they're by no means an anomaly in this space. So we've got a whole bunch of different companies with logos you probably recognize, solving problems from networking to profiling, tracing, even security. So Google's introduced this BPF framework called the kernel runtime security infrastructure. And that allows you to write BPF programs to detect combinations of events that are happening on your system, maybe anomalies, and generate some sort of event or some sort of trigger from that, and even run other BPF programs reacting on that to then take action. So you can do stuff like mandatory access control for security, sort of runtime security. So there's a whole bunch of interesting stuff. I would love to go into more detail on all of them, but you might say, oh, this sounds all good, but maybe I don't work for one of these big companies and I'm not really a kernel hacker. So how did I actually use this rich context that BPF provides today? So that's where Cilium comes in. So Cilium is about making kernel microservices aware, BPF. So really want to be able to leverage these superpowers that BPF gives us, this rich context, and see what can we do. So we can ask questions like, well, what does it look like to use eBPF to control and observe all of the network traffic that's running in your cluster? And we can even take this into a more concrete example, like what if we could use this context to understand which DNS queries were failing in my cluster in the last 10 minutes? And these are problems that Cilium is able to resolve, and I'll walk through momentarily about how it solves in these different areas. So the rest of this presentation is structured around first networking, and then we'll talk about security, and then later on we'll talk a bit about observability and visibility for apps in your cluster. So first up, networking. So a bit of networking 101, Kubernetes networking 101. So what's a networking plugin for Kubernetes, or a CNI? So CNI is the thing that allows pods to talk to each other inside your cluster. So what it's responsible for is when a pod starts up, it's going to create the network devices that are necessary to make that network connectivity happen. It will handle IP address management so that you can assign IPs to these different pods. And then under the hood, it needs to configure the underlying network, whether on the node or across the network, so that pods on the same node can talk to each other, but also so that pods on different nodes can talk to each other. So there's most naive implementations of a networking CNI will implement a lot of this logic in IP tables in the kernel. And what that does is it basically defines chains of rules that say something like, if you see this IP pass the traffic through, that's fine. Then next, if you see this other IP, okay, drop that traffic, it's not good. And then maybe you go to the next one, more advanced. It may look at the packet and say, oh, I need to change that packet in some way. Let me just do that and then send it over here. So we'll talk a little bit about why that's not the greatest approach shortly. But first, how is Cilium different here? So Cilium, rather than using IP tables as the basis for its data plane, it uses eBPF. So one of the points I want to make here is with microservices, distributing your apps into smaller pieces running in different locations inside your cluster, the networking layer is really becoming the heart of your application. So its health is correlated with the health of your overall apps, right? So what you want to do is get an efficient networking layer in there that can allow your apps to talk to each other freely. And even more than that, when something does actually go wrong, we want to be able to understand what happened and react to that in an efficient way, right? And that's what's different about BPF, is because it's got that rich kernel context. It's able to provide deeper insights into what's going on in your cluster, and at the same time do the actual networking control in an efficient manner. So Kubernetes services are one of the areas that Cilium is able to optimize. So briefly, what is services about? So services provide consistent IP addressing for applications to talk to each other within the cluster. So if app 1 wants to talk to app 2 here, it's possible for app 1 to figure out what the IP address of one of those app 2 pods is, and connect specifically to 10.0.1.11. But then it's reliant on the existence of that particular pod existing at that particular location in your cluster. And then, so if that pod goes away, maybe it's scaled down, or has rescheduled to another node or that sort of thing, then app 1 now needs to know about it if you're directly connecting these applications together. So services allow you to put this durable abstraction in the middle, which says, here's a consistent IP that you can connect to. And regardless of how your backends are scaling behind the scenes, app 1 only ever needs to know about talking to this particular service, like this cluster IP. Then under the hood, the networking layer of Kubernetes is actually performing the translation, so that when app 1 talks to the cluster IP, the actual traffic gets delivered to one of the active backends that exists in the cluster. Why is this important? Well, in a cloud native world, things are much more ephemeral. Pods come and go. The IP addresses are not always consistent for pods. You may need to scale up or scale down your services. Even just the raw scale of your environments may be much larger than it has been in the past. And again, like a lot of these implementations that are out there today would actually base the stuff on IP tables, which it has a few problems. So the main problem that IP tables has is it uses a linear list of rules to determine the networking and forwarding behavior. What does this mean? This means that depending on the number of services and the number of backends that you have for your networking, each individual packet that runs through the system has to hit each one of those rules to be able to figure out which of the services it needs to route that packet to. So that's more execution. That's more like CPU cycles being spent on each individual packet because you have to do that iteration. And that can translate into a less efficient network. You're spending more cycles on that, so you can't get as much throughput. It can also translate into higher latency for requests going through your system because you're just spending that time executing services, executing the service iteration logic that is maybe not otherwise necessary. But with a BPF-based approach, what we can do instead is implement this using a hash map. So what we do is when we get that packet coming in, we do a lookup of that service, and we do an O1 lookup. We just immediately find in the hash map which backend we need to route that packet to, and we just send it off to that destination. One of the other big changes between these two different models is in an IP tables world, when a change occurs in the cluster, the way that it implements that change is it actually has to dump all of the rules out of the kernel into user space, and then it has to add the rule onto into that list, and then dump that entire list back into the kernel again. So the operation for making a change in the cluster, like a backend scale out or a new service, is quite expensive. Whereas with the eBPF-based approach, we can just update that map, and it's a very short and simple update process. And this becomes more, this kind of problem becomes worse as you scale in a variety of different dimensions, right? If you have more pods, more services, more nodes, or different ports being used on those nodes. So I've talked a little bit about services in terms of the connectivity between applications within your cluster. But what about when you want to connect to something outside your cluster? So this may be something else in your VPC or on your physical network, or even like the outside, like the internet, right? So as a previous example, like everything's kind of under Kubernetes control. So in a lot of ways, that's easier because Kubernetes can prescribe how things work within the Cilium, the Kubernetes managed nodes. But how do you actually get traffic in and out of your cluster? We can't use that same approach. And there's two problems we kind of need to solve here. And one is how do we attract traffic to the cluster? So how do we advertise out to say, you can send traffic to this location? And then secondly, how do we distribute the traffic that comes in evenly across the replicas inside of our network? So Kubernetes doesn't come with a solution for this whole problem by itself. What it does have is it has a few kind of primitives, like for instance, the node port. What the node port allows you to do is expose a particular port on each node in your cluster. And then it'll figure out how to get any traffic that comes to that port on that node. It'll get it to one of the pods within that node. And maybe naive implementation, some of the cloud integrations even will build on top of this. And so they'll perform the advertising piece and attract the traffic to the node. And it'll be like a dedicated load balancer node. And then when it actually wants to make that load balancing decision, it just load balances to one of these node ports somewhere in the cluster. What that means is like the traffic distribution is not necessarily correlated with the number of pods that could handle that traffic, but rather with the nodes in your cluster. So in this particular example, what we have is we have 2/3 of our capacity for handling the traffic in our cluster on the node 2. But only 50% of the traffic is actually being sent because it's just splitting the traffic evenly between the nodes. So the problem here is they're not pod aware, or they're not really aware of what's going on in Kubernetes world. They're just aware that, oh, there's some nodes I can send some traffic to. So what's different with a Cilium mode is Cilium has that deep integration with both Kubernetes at the control plane layer and also with the kernel with eBPF at that layer. And so it's got that real deep understanding of where the pods are in the cluster, and it's able to make intelligent decisions about how to route that traffic throughout the cluster. So there's a couple of different models that are supported here, and one of them is you basically run this load balancer logic on each node within your cluster, and it will handle and figure out how to route the traffic to the right destination with the pod for that backend. Or the other approach is actually with recent releases, you can run Cilium's load balancing as a standalone node in your environment, and that maybe can be a stand-in for expensive hardware boxes in your physical network. And we support a lot of the features that you might want to see there in terms of fault tolerance and that sort of thing. So I've put maglev here as one example where we do consistent hashing in the load balancer, which basically allows us to route around node outages within your cluster. I'm not going to go into a deep explanation of what that is, but if you're curious, check out some of the Cilium.io blogs. We've done a deep dive on this in the past. So what else is interesting about networking with Cilium? So Cilium has a mix of users. We support a wide variety of platforms, whether you're running it or in the cloud. And we've learned a lot about integrating Cilium as a CNI into these different environments. And I think the result of some of that is you have things like GKE now is actually shipping Cilium as a default for new GKE clusters. So this is part of what they call the data plane V2 effort, which is really what Google's vision for the future of networking Kubernetes is. In addition to that, we also support in other environments like EKS. You can integrate with the cloud IPAM that's going on there. So we can allocate ENIs to individual pods in your cluster. And this can make it easier to manage the connectivity between your microservices and the rest of your VPC. And increasingly, we're seeing users wanting to run multiple different clusters. So maybe organizations have a dedicated team who's responsible for shared services, like your credential management service. And then you have other app teams who run their own clusters, and they maybe use those shared services. So what Cilium can do when it's running in these different clusters is present the Vault service, for instance, into each of the clusters for your app teams. And then your apps just need to connect to that service. And Cilium will figure out the details of the networking to figure out how to get those Vault requests out to the underlying Vault service in that shared cluster, which is managed by that common platform team. And beyond this, Cilium is also able to define policies, both within those clusters and outside those clusters, in terms of how the network policy should work. So you could define policies against particular pods and say, pods can only talk to this Vault service out in that other cluster, and nothing else in that other cluster can it talk to. So that's kind of touching on the kind of next section of my presentation here, which is about the security, right? So most advanced networking plugins will provide some sort of network policy implementation. So again, these are typically built on top of IP tables, so they have a lot of the same problems that we discussed in the previous section. So what Cilium does differently here is it provides a stronger identity-backed policy. So it's able to pull some of that context about knowing it's this particular pod with these particular labels that's making this request, and get that deep understanding of the traffic flowing through, and then write policies against that. So this slide talks a little bit about, in the top left, we allocate these identities to associate with individual pods in your cluster, like a front-end identity for your front-end pods and identity for your back-end pods. And then using eBPF, we can actually associate that identity with the packets as they flow through your underlying network, and then use that identity to perform network policy even at the destination. So we use that rich context to provide a more secure policy implementation. And this is talking about multiple layers as well. So I talked a little bit about what you talk about, like layer 3 and networking there, where we're talking about like apps with label front end talk to apps with label back end. And of course, we can support that with ports as well. So you're only allowed to talk to port 80, front end to the back end. But we can also extend this up to the layer 7 level. So only the front end can make GET requests for /public to the back end. And if it turns instead makes a put request to /secrets, then that's going to be denied, and it's going to be denied in a like a protocol specific way, which is to say like send back a 403 forbidden message back to the source and say like, no, you're not allowed to do that. And that's locked down before the request even makes it to the back end. So what about connecting to resources outside the Kubernetes cluster? If we, in the previous examples, we're kind of defining based on labels of pods. How does that work if I'm talking to mydomain.io? So Cilium has what we call 2 FQDN policy, or 2 fully qualified domains. So we can actually match on traffic to a specific domain and then only allow that traffic. And the way that this works under the hood is we observe what's going on with the DNS requests under the hood. So your front end, when it tries to talk to www.mydomain.io, the first thing it'll do is like, oh, what is the IP of www.domain.io, mydomain.io? So it'll make that DNS request out to the kubedns or core DNS instance in your cluster, which will then respond back and say, oh, here's the IP address. And then after that, it's able to make the actual connection out to that particular IP address. So with Cilium and with eBPF providing that visibility inside and what your application is actually doing there, it's able to then use that context to say, oh, this application's trying to connect to www.mydomain.io. So I'm going to allow that traffic. And the nice thing about this is it says like, we're talking about semantics of who this is trying to talk to, like mydomain.io, rather than talking about like a particular IP address, which is just a location somewhere on the internet. So if you're curious a bit more about that, definitely check out networkpolicy.io. So, Cilium is able to do, basic IP insider-based policies. But in a lot of ways, what we're trying to kind of lift the conversation about is to say, we should be able to define the network policy and the policies for traffic flowing in your cluster at a higher layer of semantics that give a richer sense of, this particular pod is allowed to talk to things that have this label, or this pod is allowed to talk to things in my VPC with these particular EC2 labels, or like the DNS names, for instance. Yeah, so if I've done a half decent job here, then maybe I've convinced you like BPF is the future. It's a sensible data plane for your networking, for your Kubernetes clusters, and Cilium provides the networking piece, and it allows you to lock down the security of your cluster. But the question is like, what happens on day 2 when you need to support that cluster? And that's where I want to tie back into observability and how like context is really king. And how if we can expose that context about what BPF knows is happening in your kernel and in your applications, then you're going to be able to better support your apps in your environment. So for the purposes of this discussion, like we're going to define observability about basically having the tools necessary to observe how your applications are behaving in your Kubernetes cluster. So, I want to be able to ask, can I see the traffic that's flowing between these two applications? When traffic is dropped in my environment, show me why that's being dropped. What is my application actually doing here? And maybe like when there's different sets of events going on in the cluster in different places, do I see an increase in errors when those conditions occur? And can I measure those and show them in the dashboard somewhere? And there's even like the classic question, like, is it DNS? Kubernetes doesn't provide a lot of tooling to answer these questions, and in fact, most networking plugins don't. So that's where Cilium and Hubble come in. So Hubble takes everything we've learned about the applications, about at the app layer or at the networking layer, and it exposes to you in 3 different ways. So we have a UI, which can provide service dependency maps to say, like, here is the flow of traffic between different pods in your cluster. And you can like dig into the display and filtering of those particular flows or those particular pods. We also have a network policy viewer there. So you can reason about the way that your network policy impacts your apps in your cluster. Secondly, we have a CLI, so you can get like detailed information about individual flows that are going on in your system, or do more advanced filtering or get JSON output and start to process that somehow. And the third category is around metrics, and so exposing not only what's going on in that cluster, but also attaching that deep context and that understanding of the pods, labels and context, and attach that to your metrics as you're exporting it to Prometheus and Grafana and so on. So this is one thing that gets a lot of people, I think, excited, is to see the Hubble UI that we're able to construct on top. This is just like a simple example of the service map functionality. So we've got the job posting app here, and you can see the way that, say, the recruiter and job posting are connecting to the core API, and then the core API talks to Elasticsearch, and so on. And so we're able to like at least just like visualize, what is that's going on in the cluster. And then when you double click into those different pods, you can start to see a breakdown of the individual flow data. So normally I think I'd prefer to do an actual demo and kind of show you interactively, but unfortunately I don't think I have time for that today. But I will give you at least a sense of how that stuff works by digging a little bit into the CLI. So on the Hubble CLI, like I have an example on the left here, and what we're doing is just like Hubble observe -- follow to see events as they occur in your cluster. And we're filtering by labels. So any pods with the label class equals X-Wing. So we've got this X-Wing pod that's flying around somewhere in the galaxy. And so it wants to connect to Disney, www.disney.com. And so the first thing it's going to do is it's going to do that DNS request. And so you can see around about the middle of that box, you can see the DNS requests flowing out to you can see the namespace and the name of those pods. And there's a bunch of more deeper detail you can dig into with more advanced CLIs here as well. So once it's resolved www.disney.com's IP address, is then able to establish that HTTPS connection out to Disney.com, right? And so the second sort of batch of flows there are talking, you've got the application reaching out, and the way that it's presented, you can see it's like the X-Wing pod is reaching out to www.disney.com. So it's not just saying like this IP is reaching out to this other IP, which then you need to do that extra layer of analysis to understand like what does this mean, like what is this IP, what is this IP. But Hubble, like built in, it just provides you that context, and it just says like it is this particular pod trying to reach out to this particular domain name, not just an IP address. And then, maybe later on the X-Wing, gets some idea in its head, and it figures like, hey, I want to go check out the Death Star. But of course, the Empire is a little smart to this by this point. So what they've done is instituted a network policy to lock down the Death Star. So the X-Wing isn't allowed anywhere near. And so we can see in the very last line of that output, we have actually a policy denied. And so there we can see like Cilium is actively dropping this traffic. And the reason it's dropping this traffic is because the traffic doesn't match the policy. And so it's really like key insights about, not just the packet is being dropped, but also the packet is being dropped from this pod to this pod, and here's why. And so there's a whole range of different metadata we can pull in, and a lot of this is using the context that BPF provides us. It can be stuff like, your individual packet headers at different layers. It could be the pod, names and labels and so on from Kubernetes, or DNS names if we're monitoring for those, and even also of course the Cilium insights as well. Things like which identities are involved with these pods. Why are we dropping this traffic and so on. So looking at the, is it DNS kind of a question, right? We have an example here, and it looks a little bit complicated, but it's actually not all that complex. So on the first line, we have like Hubble observe, and we're looking for L7 traffic here. We're going to output in JSON format and then just follow the flows as they get sent through the cluster. And then we're piping the output of that observe command into JQ and just running some simple expressions against that. So what we're doing is we're selecting any flows there where the return code of the DNS request looks like it's an error. And then once we grab any of those flows, we just format out the destination namespace, destination pod name, and then a summary of what that error was. So when you run this command, and in the cluster, what we see is like a flood of Jar Jar Binks trying to connect out to some unknown galaxy. And so, it does a whole bunch of different requests, but you can see like each time that it makes these requests, the reason it's getting rebuffed is Jar Jar Binks is trying to reach out to a non-existent domain. And we can see that very clearly from the CLI output here. And again, like it's not just that we see that these DNS errors are occurring, but we're also able to tie that back to, it's the Star Wars Jar Jar Binks app that's actually trying to make that connection outwards. So taking this even a little bit further, we're able to provide even more visibility at the application layer if you enable the proxy visibility. So what this does is it sends traffic through a per node proxy, which can then introspect like deeply the HTTP or gRPC or protocol specific data, and it is able to export that context along with those flows again out to Hubble and out to your UI CLI and so on. So in this case, what we're seeing on the right-hand side there is you can see like we've got a response. In this case, the response actually had a latency number versus the request that was originally made. And of course, we can do calculations across that and like map that and make metrics and so on. We're seeing stuff like, your method, your URL, your deep headers. So we're really getting that kind of deep visibility into what's happening at the network layer. So what happens if the traffic is actually TLS encrypted? So in this kind of use case, I'm thinking about your app talks to some external service. Maybe it's like www.github.com. So what it's going to do is use like standard TLS libraries, OpenSSL or LibreSSL, whatever, and it's going to encrypt the traffic as it goes out from that pod, as it's sent out to that, something outside your cluster that you don't control. So if it's if the pod's encrypting that traffic, like how do we get that visibility in that case? It just it doesn't really make a lot of sense. So most existing commercial solutions for this sort of thing would do like a man in the middle. You would deploy a dedicated box somewhere, and you establish the connectivity basically from your pod service to that middle box, and then from that middle box out to the outside world. And this usually involves injecting root CAs into your containers and stuff like this. What we're actually able to do with BPF is we can leverage this thing called kernel TLS. So kernel TLS simply it keeps the control, like the complex control plane pieces of TLS in user space as part of the SSL libraries, but then it moves the actual per packet encryption process down into the kernel. So it's offloading there. And the background to that is like large cloud providers wanted to do this to increase performance. So now that we've pushed the kernel, the actual encryption step down into the kernel, then using BPF, we can actually defer that encryption until after we make the visibility check against that traffic. And so from your app's perspective, it's just using a standard library. It's just connecting out the way it always has. But under the hood, we're actually able to defer the encryption and give you the visibility and insight into your traffic as it's flowing through the system. And then again, on the outside world, nothing's changing there either. If you're more curious about this, there's a link in the slides, and I can share those afterwards as well. So finally, the third category I talked about with Hubble was around metrics, and so this is about like exposing standard metrics APIs to be able to introspect stuff that's going on. So this can be stuff like metrics for flow events, like your HTTP events going on in the system. Looks like maybe that link is on the slides not quite working at the moment. I'll follow up with you after and get you a good link for that. Yeah, the cool thing about this is, like, again, we're gathering that deep context and that, both Kubernetes pod context and also like what's going on in the kernel, and we're aggregating that together, and then we're able to export all of that data together through Prometheus endpoints, and then your standard Prometheus setup is able to pull that, and then you can graph that in Grafana and so on. So I think if you look at maybe if you search for the Hubble announcement blog, you'll actually see a whole bunch of cool examples there. Around specific use cases, like maybe I want to see when pods make requests out somewhere, but there's never a response. And so there's a bunch of different cases that this can help you to identify what's going on in your cluster. So kind of rounding out, I think the presentation now. So there's a whole bunch of functionality that Cilium provides. But the bottom line is, like, BPF is just providing a way for Cilium to gather such rich context to be able to connect your applications together efficiently, but also to understand what's actually going on in your cluster and reason about how applications are behaving and resolve network issues there. So this is not a comprehensive list by any means, but just a few of the highlights. I'd be happy to talk about any of them later on after the talk. And maybe just to give you a little bit of insight in the parting thoughts, is Cilium kind of production ready? Is it ready for you to run? So we have a wide range of actively engaged community members who are building on Cilium today and using it for production workloads. And this can be a range of different users. This can be providing infrastructure to others. We have like live radio, we have banking and financials, and even like gaming services are running on top of Cilium in production today. So there's a bunch of cool stuff. Thanks everyone for listening. If you're interested to try out Cilium, I'd suggest going to www.cilium.io. We have resources to learn more. We have getting started guides, both for just like bootstrapping, getting Cilium up and running, but also for specific use cases like security, policy, and so on. So you can use that to explore further. And yeah, I'll be around if you want to chat or you have questions. Feel free to reach out.